Good afternoon. Welcome to the 8th Pancharatnam lecture, launched during the Platinum Jubilee of the Year of Raman Research Institute. These colloquium-level lectures are a part of a prestigious named series instated in honor of Professor Pancharatnam, an illustrious alumni of this institute. So Professor Pancharatnam joined the Raman Research Institute as a senior scholar in 1952. He completed his PhD under Professor C.V. Raman. So he was interested in crystal optics and discovered a subtle effect in the interference of polarized light, which is often referred to as Pancharatnam-Berry phase in quantum mechanics, pertaining to the geometric phase, relevant both in classical and quantum optics literature. In fact, when brought to his notice in the mid-80s, Professor Michael Berry showed the true scientific largesse and immediately published an article titled On Pancharatnam Phase to draw attention to the pioneering work done 3 decades earlier. RRI has continued to be very active in this area, and I'm proud to say we are one of the really leading research labs in quantum topics and quantum experimental topics. Personally, for me, I was very surprised when visiting expert in CMB experiments pointed out that Professor Pancharatnam also devised the first achromatic wave plate for his optics experiments. This was recognized and soon ported to infrared, and more recently in the current generation of cosmic microwave background experiments. Professor Pancharatnam tragically passed away in Oxford on May 1969 at a very young age of 35. So we are honored to be able to, have these lectures given by the top scientists in the field. And I'm really happy that we have a Dean of Astrophysics, Astroparticle Physics, and Gravitation, Professor Roger Blandford here. I'll invite Prajwal to introduce the speaker.
So it's my great pleasure and privilege to introduce our speaker today. Professor Roger Blandford is a distinguished astrophysicist who has made highly influential contributions to our understanding of the high-energy universe using theoretical, computational, and empirical approaches. He has covered a very wide range of astrophysical problems, mainly the physics of black holes, but also neutron stars, white dwarfs, gamma ray bursts, and also the phenomena of gravitational lensing, shocks and acceleration, magnetoluminescence, and cosmology. Roger's pioneering work was on the twin exhaust model to explain what in those days were somewhat unimaginatively called double radio sources that straddled galaxies. He then brought us the Blandford Pane and Blandford's Night processes for the production of jets from black hole systems, and they are the best explanations to date for the production of jets. And then the Blandford-Koenig model, which was a landmark in deepening our understanding of these systems via the systematics of accreting supermassive black hole. A later landmark was the application of general relativistic magnetohydrodynamics to computationally simulate astrophysical jets, and which he did with his team of students and postdocs. Roger got his PhD from Cambridge University with Martin Rees and was faculty at Caltech and later at Stanford, where he was the founder director of the first new Kavli Institute. And he's currently the Luke Blossom Professor in the School of Humanities and Sciences at Stanford. Apart from his scholarship, he chaired the US Decadal Survey of Astronomy and Astrophysics in 2010. He has won a slew of awards, including the Helen Warner Prize for Young Astronomers, the Dana Henneman Prize for Mid-Career Astrophysicists, the Eddington and Humboldt Medals, the Crafoord Prize, jointly with Roy Kerr of the Kerr metric fame, spinning black holes are key to the production of jets via the Blandford process. And more recently, the Shaw Prize. And of course, the most valued legacy, he has mentored many PhD students and postdocs and other students and has been mentor at large to many astrophysicists across the world. Roger. I hope you don't step on the wire.
Thank you very much, and Professor, I'm humbled and thank you, and grateful for your very kind introductions. And I just say how pleased I am to be back in the Raman Research Institute. It's been far too long since I've been here, but I had many happy memories of being here since the mid-1980s, especially with Professor Rajakrishnan, who at that time, who I got to know. And I'm also deeply honored to be giving the Pancharatnam lecture because I really did not know much about him until I read Michael Berry's article, which you referred to, and he clearly was a remarkable scientist, taken from us far too young. There's optics in this talk, and this is just a humble tribute, if you like, to Pancharatnam, and because he obviously was not just one thing, he was obviously very broad in experimental and theoretical optics, and I'm very happy to be here. What I'm going to talk about is actually a combination of general relativity, electromagnetism, and optics, I suppose. And it's quite a mountain in astronomy. But in preparing this talk, I've been unclear as to what to emphasize, and I've tended to remove a bit of the astronomy and sort of put a bit more physics in, because I know there are quite a few general physicists here, so it's more in the language of physics. I also got some slides that have got a bit more formalism in them, and I'm quite happy to skip straight through them if they're boring people and they don't really understand or whatever. And there's plenty of material here. So I'm very comfortable if people ask questions during the talk, because that'll give me some clue of how to proceed and what to emphasize. So please feel free, especially the young people, feel free to ask questions during the talk. I'll perhaps explain my title. Those of you who eat breakfast in the United States and probably all around the world may have heard this phrase. But in case I get tapped for proprietary, impropriety, yes, I should also point out that it has a physics and engineering connotation, because you may not know this, but in addition to position, velocity, acceleration, and jerk for the going as far as 3 derivatives, then if you wish to go to the 4th, 5th, and 6th derivatives, they are called snap, crackle, and pop. Why? I'm not entirely sure. Why anyone would care about this, I'm even less sure about, but apparently that's the case. I once read a paper on cosmology that used this. Anyway, but it actually is the 3 topics, the three features of what I'm talking about here. It struck me that that actually described in some figurative way what was going on. And so what it's actually about is one of the most publicized images in recent times from astronomical telescopes, which is the great giant orange ring orbiting a black hole in M87, a nearby elliptical galaxy. And what I'm going to talk about here is a heterodox, that's a polite word, view of what might be happening in that particular source. There's a sort of standard interpretation, and I'll try and explain this. And I do this not so much in the spirit of those people must be all wrong, listen to me. It's more in this is an alternative. And I think what particularly is appealing to me is that unlike many such alternatives one sees in astrophysics today, I think it is refutable, in the sense that, you know, observations, in fact, using existing data can actually sort of say, well, there's no sign of that whatsoever, so maybe the first idea was right all along. So it's that very much in that spirit that I'm doing it. But that, I hope, will become clear as we go along. What I'm talking about to some extent has involved these people here, and I'll maybe mention them a little bit more down the road. Historically, I've worked with many, many people, but in particular, my ideas have been framed a lot by former collaborators I've listed here, and there are many more to add to that. So let's go on the first slide. This is, I think everyone must have heard about this, the Event Horizon Telescope imaging of M87. This is very nearby, a giant elliptical galaxy. This is the sort of more current list of telescopes that are used, distributed around the globe. It's not all of them, but it's the ones that are used the most current up. And the big change is adding getting this telescope to work in Greenland, which has helped quite a lot in the imaging. And I just want to say up front that this is a tremendous technical achievement to get all of these telescopes to work together, even harder to get the agencies responsible for them to work together, and then most of all to get the astronomers who use them to work together. So it's a tremendous accomplishment to do all of this, and a huge amount of hardware had to be built to do interferometry across the globe at a wavelength of 1.3 millimeters. You don't have to know much radio astronomy to know how hard that is. And now they're getting fringes at even shorter wavelengths. No results as yet, but they're on the way. There's many other sources that have been seen, in particular for the non-astronomers here. Sagittarius star is the black hole at the center of our galaxy, less than 1,000th of the mass of M87, but the same angular size. Also doing polarization observations, much else going on in many other sources. So, you know, this isn't just one thing, it's going on. There are data that's been analyzed at different times here, and so there are variability that's seen, and you would expect it. And then M87 is the first nucleus of a galaxy, which we now know contains a black hole, tiny little thing in the middle of this giant galaxy, to make jets. And that was discovered by Heber Curtis over 100 years ago at the observatory. And you see this on different scales here. The black hole's hidden in there, and as you go to larger scales, you see this jet coming out. Before it was just a featureless line, but now you can see that the emission in this jet, and this is something I'll return to, is coming from the walls of the jet. And we'll come to that down the road. And then surrounding this is a giant cluster of galaxies with lots of gas in it that has to be kept hot. This is how it's kept hot. This is the heater. This thing that's more about the size of the solar system is making something about 6 million light years across. It's keeping it hot. Okay, so that's probably enough of that. And as I say, please ask questions if we go through. This is shortly structured, so I can just drop material if I'm not finished by 3 hours. Okay, all right. Yes, question. There you go.
No, just a cue. So that polarization image that you showed, it has some features.
Oh, yes.
I'm wondering that all of these should have similar feature and then
Well, there's polarization observations of Sagittarius star, which are actually more interesting, as well as M87. This is actually rather confusing. What is shown there is for some unconventional reason the electric vector of the polarization after removing Faraday rotation and so on. And that's not what you normally show. But anyway, this is telling you what you see after you remove foreground effects. Okay, but there's more information there, and it's quite good. Yes, a question.
very nice question. So where is M87 here? This is a cluster of galaxies on the left?
M87s in the Virgo cluster.
No, but in this picture, I just want to get the scales.
M87. This is in the thank you. This is the nucleus of a galaxy.
Okay.
So a galaxy is a very big thing.
Yes.
And then it's surrounded by a cluster of galaxies, which is even bigger. That's about, got a radius, the outer radius of this thing.
So
is
the
about 3
first,
million light years.
so the first picture is a cluster of galaxies.
No.
This
This is inside the galaxy.
All right.
So,
Okay.
okay, to use astronomical jargon, 25 kiloparsecs.
Oh, that's not
The
very much.
cluster is 2 megaparsecs, and its distance from us is 70 megaparsecs.
Okay.
Okay, so it's a big thing. So we're down here, and we're something that's at the size of the black hole size is the size of the solar system. And it powers the whole thing. So it's even more impressive than a nucleus in terms of scale. To have this tiny little nucleus inside a great big atom. This is even more impressive in terms of scale. Question?
Yeah, I'm struck by the range of nebular structures in the first image,
That.
Can you say a little something more about that? Yeah, especially where your pointer is right
Yes,
now. Are they?
Yes, this of course this is on the largest scale, and this
Yes.
is historical. But you might like to think about this as some backflow.
Yes,
making
precisely.
Making a vortex ring at the end.
Yeah.
That's the way it would be modelled and interpreted.
Okay.
But really, what matters is what happened long ago. I don't want to.
So are they super bubbles caused by supernovae and?
No, this
there
is a
aren't.
jet.
Okay. Oh, okay. You're looking at jet.
This is
Okay.
this tiny little black hole is powering it, in a mighty quasar. A tiny little black hole in the middle of a giant galaxy
Okay.
produces up to 1,000 times as much power as the
Okay.
all the stars in that galaxy.
All right. Thank you.
This is sort of impressive. And I don't want to offend M87, but today it is kind of pathetic. In its past, had you been here to observe it in its prime, it would have been the brightest star in the sky, and brighter than Virgo. Brighter than Vega, sorry, I meant to say, which of course wasn't around then. So it would have been very bright indeed. Now it happens to all of us. But that's what went on. Okay, all right. So, yes.
Black hole is at where are the nearest star?
So the black hole is in there.
These pictures, are there further stars in here or?
Oh, no. Well, there are stars around, but on much larger scale. Okay. So this is this is the size of the solar system. Okay. And when you've got 1 billion times the mass of the solar system there, a star feels rather insignificant. Okay. When I first saw this image, well, actually, not when I first saw it because I was a referee, but when I was allowed to see this image, I sent it to my collaborator, and I said, this is amazing. We should think about this. And her reaction was immediate. So this was our first model. He said it's all a scam. So I countered with a bit later with mine for those who read Tolkien and so on. Maybe not. Okay, all right. So at any rate, let's go back in history. This old ideas of ways about black holes, how they behave when they're fed with gas, basically was to say that there was an orbiting disk of gas around, because the gas would have angular momentum, a bit like Saturn's rings and so on. And so there'd be orbiting ring of gas. There would be friction in that ring because there's differential rotation, and the gas would fall inwards and release energy. And as if you've got a black hole there, you can get some good fraction of c squared out per unit mass in terms of the power that you make. And so it's extremely efficient, far more efficient than nuclear power, for example. Okay. So, but the way in which this happened was rather controversial. And this was an old idea that Miss Beagle and Martin Rees and Delphine and I worked on a bit, and others. And I call out Rajaram here, who's here in the audience, And he was doing it in a slightly different context, but thinking much the same thoughts, and there were others as well. And basically the idea was there are two regimes when the gas falls in and has a hard time of getting rid of the energy that's released. In one regime, it's when there's a lot of gas there, and the photons are trapped, essentially, and they can't get out fast enough, and so they're sort of carried into the black hole. In the other regime, it was conjectured that the energy that was released went into the ions, and the electrons remain relatively cold. And the ions have a hard time also releasing the energy. And if the electrons remain cold, then the ions have a hard time getting rid of the energy. And so again, the flow is more like an adiabatic flow rather than one that is radiating. And you would expect then the pressure to build up and to make, these are sort of things that we drew at that time. They were only sketches. Then there'd be a black hole, then accretion torus, and then and these are sort of slightly analytic, semi-analytic models and so on. And there's two things to draw attention to here. One is the jets are essentially formed by a large funnel, and a bit like a pea shooter that sends out the jet. And the other is that the power, in this case, comes from the spin of the black hole. And I'll say a bit more about this down the road. So as Prajwal said, you get spinning black holes, and if you stick magnetic fields, the magnetic field crosses their horizon, then you can take the spin energy out of the black hole, just like you can in a pulsar, and power the jets. So I'll come on to that again a bit more, and as I say, this idea was developed. And it is, for, I think, most of the people working in this business, they have sort of developed this in wonderful ways, particularly using numerical simulations. So numerical simulations have been used to describe how the gas flows around here, how the jets form, and so on. And here are, somebody who I work with not so much on this topic, but on other topics, Ramesh Narayan, who everyone knows well here. And I've just taken some of he's done all of these papers, and basically you imagine some physical prescriptions for describing the behavior of the gas and the acceleration of particles to do the emission, and then you compute what the physical conditions are in this torus here, what the emission is that you would see, and so on and so forth, and then you try and fit the data. So what you're really doing here is you're taking an ion pressure supported torus, and it collimates the jets, and it's what, more generically you call forward modeling. So you make this microphysical thing, and then you calculate with sophisticated algorithms what would happen, and then you compare with the data. Okay, this is sometimes called MAD accretion here, where MAD is an acronym, essentially magnetically arrested accretion, and a magnetically arrested disk, so it says the magnetic field is dynamically important in this region and arrests the inflow of gas, but it keeps on flowing in. And just to give some round numbers here, the magnetic field strength in these models, and there's huge numbers of papers written on this, doing different simulations and so on, and they're typically round about 10 Gauss. I would use numbers very loosely in this talk. And that's in the jet here, and then in the torus, they're weakly magnetized. It's just the ion pressure that's the dominant thing that's holding it up. Okay, so let me just give you some numbers here to give you some scale. Firstly, the mass is about 6 billion times the mass of the sun. Okay, it's not the most massive black hole we know about, but it's right up there. And this, if you know if you just do GM over C squared, gives you a corresponding distance, and that is going to be 10 to the 15 centimeters, 10 to the 10 kilometers. That's the size of the solar system, and the corresponding time scale dividing by C is 8 hours. And then the corresponding, if we say, let me just go back, I should probably go back to the first slide, just draw attention to something. Yeah, I want to draw attention to something here. Having got this here, we've got gm over c squared, and this is that unit of length, and I'm going to use that henceforth as the unit of length, gm over c squared for the black hole, taking the measured mass. This is what it looks like on the sky, and then I'm going to, let me just orient you. It's a little bit complicated, this, if you don't think in 3 dimensions, but this is what it looks like on the sky. What is actually, I'll come to your question in a moment, but let me just perform this. If you remember, I said there were jet there, and you may have seen there were 2 jets. So there are basically 2 jets here. There's the one that you see prominently, this one here, that one there. That's the one that's brightest because it's got material moving relativistically in your direction. So to take an example, if Prajval is the observer, which he really is, then, and this is the black hole, conveniently enough, I've got one jet like that and another jet like that going in the opposite direction. Okay? This is the orientation. And what astronomers have basically concluded is, and I can explain the reasons why, is that the black hole is spinning with the sense of its angular velocity being along the counter jet. So the inclination and the angle between the line of sight from my black hole to Prajval and the direction of the spin axis is going to be 163 degrees. Now there's probably a large error. There is a large error on that, but that's the sort of nominal number. So it's around about 20 degrees between the one in the opposite direction and that's the one she's seeing, this jet. But the spin is into the sky, and that will help you orient you as we go down the road. So that's the point I should. Oh, and I should say one more thing, and then I'm going to use x and y or u and v coordinates. I can't remember which one I was using. Y is along the spin axis, and x, the projection of the spin axis, sorry, on the sky. This is what you see on the sky. This is the sky, what the astronomers would call the sky. This is what you see on the sky, and x is perpendicular to that. So y is along the direction of the spin axis. So that's what I'll be doing. Okay, so here we go. We go through that, and here's the number. So let's go on to spin, and I'm going to treat this in a way that's a little strange for others, but some of this is going to be a little strange. I'm treating this as basically as a 3 vector in space. And because I'm setting m equal to 1, A has got to be between -1 and 1, and it's presumably it's prograde. It's argued that it is prograde for good reason. That's the angle that I was giving before, and I'm just purely guessing at this point that the spin is about the angle. This is the spin angle. A is the angular momentum. This angular momentum is 90% of the maximum it could be. Okay, and just let me finish that, and that means there's actually rotational energy there, which is there for the taking, which is 2 times 10 to the 56 joules, or 2 times 10 to the 63. Oh, that's enough to keep the surrounding cluster of gas going for 1 trillion years, much longer than it needs. And you, sir, I forgot to answer your question, so please ask it.
My question is about the cluster of gas. You said there's a high density region where the photons can't escape. Right?
This is if you supply lots and lots of gas.
Yeah. So
this is one. This black hole in M87 today, or at least when we're looking at it, is being starved of gas. It's got a very low supply of mass.
But in a situation where it has a high supply of gas,
very high supply of gas, then you get all this radiation which is trapped.
So is that the Hawking radiation?
No, it's nothing to do with Hawking radiation.
Okay.
Hawking radiation is only relevant for very small black holes, or for ones that are imagined by theoretical physicists, where it has been amazingly productive. So it's been a real touchstone for theoretical physics. But they've never been seen as yet. So these are only very tiny black holes, as big as the mountain, as heavy as the mountain, not as big as, but as heavy as the mountain. Okay, thanks for that question. Okay, so this is a huge power here, and so huge power. Now, here I'm coming to a follow-up question. This is good, okay. I'm clearly going to slide 5, and I thank you, because I'm not sure I prepared the rest. So, okay, keep on going. Sorry.
So for photon trapping to occur, the accretion should be how much high? Like how many Eddington?
Yes, thank you. You asked. There's a reference luminosity and power supply, which is called the Eddington level or Eddington rate, and there's a corresponding mass supply rate. The M87 regime, where you get the ion-supported disk, happens. In this case, it's about 4 orders of magnitude smaller than that. In the ones where they're trapping the photons, they're usually about 10 or more times that in terms of mass supply. And then there's a bit in the middle where you get boring disks that do their job in a undemonstrative fashion, except just making quasars. So, yeah. Okay. All right, good. All good questions. Please keep on asking them. And so if we look at the key thing is now, is if I take the view that we should be doing this more from the top down, from going from the observations and doing things, not building forward modelling from models of somewhat dubious basis, but actually sort of make inferences from the observations and going as far as you can that way. And for me, the estimates of the jet power are something like 600 times of the power associated with this great big orange ring. And that's the thing you could compare and measure. And if you say, well, there's a whole accretion disk there, it's probably at least 100 times that. So most of the power in this thing, it seems to be going at least 100 times, 99% of it is going into the jets, and it's not radiating. And that's a comparison that I would make. Now, I think, in fairness, we don't know that because we only know what the jets look like far away from the black hole, and it could be it's in a very low state at the moment. And that's what people say, but I take this seriously and imagine that the jets really are most of the observed power. And the other thing is, if you ask what the mass supply rate is, this can be sort of measured using X-ray astronomers, but we've done much better by infrared astronomers using Webb telescope. That is, in these units, 10 to the 22 grams per second, and that is much larger than what anybody thinks is actually flowing into the black hole. So we're supplying gas at large radius, seemingly, these aren't solid numbers, but they're highly suggestive, much larger than anything could be actually getting into the black hole. So there's much uncertainty in these numbers, but they're going to get better, but the inequalities are large. So I would say this raises many questions, but the 4 are, if you've got these powerful jets, why are the disk and the gas that's supposed to be continuously flowing inward, plunging into the black hole, crossing the horizon and saying goodbye to the rest of us? Why is that so dim relative to the power that's there for the taking? And the second is, if we're right in saying that the gas, most of the gas that's supplied goes away, it's from inside a gravitational potential well. What drives it out of this potential well? Okay. So it needs energy to do that. It's got to be driven away. It's got to be given energy. And then a third one is, if you come back here and look at these observations here, you can sort of see it here. You can see the jet being actively collimated. As you go out to a larger scale, you can measure the width of the jet. And it's being actively collimated. If it were a pea shooter, it would be going out like that. But instead, it's doing that. Something is squeezing it in from the sides. That's happening at 10,000 gravitational radii, and probably then some. So the question is, what's causing that? And I'll ask a fourth question, is one of the things that ever since the days of double radio sources, as they were called, they were always associated with one breed of galaxy, which is the elliptical galaxy, which is like ellipse on the sky, and not with spiral galaxies like her own. There are one or two exceptions, but that's still a pretty hard and fast rule. So why? So Now, if you follow this line of argument that the power in the jet is large, then you have to have a large magnetic field. And in the roundest of numbers, we would say that that had to be at least 100 Gauss rather than 10 Gauss. And again, I'm averaging over many uncertainties, but it's a high field model, and that has implications, which I'm going to sort of try to explain to you. How are we doing? Okay. So I said that they were now called mad disks, as opposed to sane disks, which you don't need to know what those are. Those are normal disks, but mad disks are magnetically arrested disks. And so the only way you can get any respect in this business is by coming up with an acronym. And so the one we use here is whole energized magnetically mediated ejection disk. I'll explain what all those things mean. So this is an alternative story that has developed with my colleague Naomi Globus, who did more than send me a picture of a cat, and a lot more, including drawing these pictures. And here the elements are. You've got a black hole here that is spinning. You have a magnetic field that is threading the horizon of that spinning black hole, extracting the spin energy, slowing it down imperceptibly because it doesn't need very much of it. That creates the jets. Which is on 4 different scales, from the largest scale to the smallest scale. So on the largest scale, it's just shown schematically here as a jet. And those jets are going out in anti-parallel directions like that. And if we look on the smallest scale, we can see in this cartoon field lines threading the horizon of the black hole, extracting the energy. And you have this region here, which is essentially purely electromagnetic. There's a little bit of plasma there that's necessary to carry the currents and charges and so on, but it's dynamically totally insignificant by 10 orders of magnitude, the minimum that you need, 10 or 11 orders of magnitude. So you have here currents and charges and just Maxwell's equations in the way that Maxwell conceived them. It's essentially force-free electrodynamics, no inertia associated with the gas. It's just magnetic stresses pushing magnetic energy density around. Electromagnetic stresses pushing electromagnetic energy density around. Now, if we think about this in naive electrical engineering terms, this is a fairly modest jet, electromagnetic jet. There's a mere 10 to the 19 or so volts across the event horizon. There's only 10 to the 19 volts. Now, you only need 10 to the 6 volts to make an electron-positron pair. In practice, you need significantly more than that, but there's a big difference between 10 to the 6 volts and 10 to the 19 volts. Furthermore, these field lines, as shown here, are not tied in a good conductor. They're slippery on the surface of a rather bad conductor. The effective resistance of a black hole is about 60 ohms. And you might say, where does that come from? Well, it comes from the impedance of free space and 4 pi. So something like about that, okay? And so you get, obviously, large currents and large voltages here. And it's reasonable, I think, without making any big fancy model or simulation, to say this thing is going to be sparking like crazy. There's going to be little flashes and lightning going on all the time. Okay, the next part of this is the ergomagnetosphere, a word that we coined. And basically what this says is that if we are going to have the black hole have not just create the jet, but have an influence on the disk, we've got to have a connection between the black hole and the disk. And there are 2 sort of generic mechanisms that we can think of. One that for doing this, one that we'll call a clutch, which is basically having field lines going through the equatorial plane, and these are going to be generically unstable. Many people here are working on sort of similar things in accretion disk. They are generically unstable, And that means there will be a transport. There's a differential rotation here. The black hole is spinning much faster than the surrounding gas. And so there's going to be transfer of angular momentum across the magnetic field from the spinning black hole to the accretion disk. That's one way of doing it. The other way is what we would call the capstan, which are loops of magnetic field, which are almost certainly transient, non-axisymmetric, and so on. And they're tied to the conducting gas in a disk, and then they're pulled forward by this pull conductor, the horizon of the black hole. Okay? And that means that you've got a capstan, which is like on a boat, where you've got a rope and you're transferring energy from the spinning black hole to the disk. So there's energy being transferred from the spinning black hole to the disk. And those are two sort of generic mechanisms. You can fancy them up and simulate them or so on, but that's generically, and it seems to us at least not unreasonable that there should be 10% of the jet power actually gets out into the disk. So that's our conjecture. There's also something interesting coming on here which is related to the so-called Penrose process, which I'd love to tell you about. This is certainly very controversial, but if somebody, we'll call it the governor, but I won't do that now because there isn't going to be time to go through it. But if somebody asks me again, I'll talk about it. So if you follow this line, this chain of thought here, that you can get power from the spin of the spinning black hole into this disk out here, say, so schematically, then what it does is solve your mass problem, because it essentially gives so much power to the spinning disk that it drives away all the gas that has fallen in. And so it drives it away, and drives it away in a hydromagnetic magnetized wind, shown schematically here and on a larger scale here. This is going to be a somewhat irregular thing, but it'll drive it away in a wind. And winds from disks are very good ways of removing gas, because if this is a black hole again, this is a accretion disk, there's a magnetic field line coming up. If the magnetic field line is vertical, and I put a bead on the wire there, or some plasma are tied to that magnetic field line, it'll just oscillate up and down. But if I put it out like that, it'll be flung out centrifugally. And that's indeed what happens in these models. So there is a wind, and so instead of being an accretion disk, which is the normal type of disk, this is an ejection disk that drives the gas away. That's the conjecture. And furthermore, if you think about the magnetic field, these are the field lines. These field lines, as they spin around, they're going to create toroidal magnetic field. They're going to create magnetic field lines because they're going to be lagged behind the disk at the foot points, and they're going to wrap around the jet. We used to say there's a current going along the jet, and that because there's a pinch, J cross P pinch, that squeezes in the jet. And this is the mechanism for collimating it all the way out to 10,000 gravitational radii. Question? Thank you.
To drive away the gas, you first have to collect the gas. So was there an epoch at which there was an accretion disk formed around?
Oh, no, it's more or less continuous. Let's just go on to the next one, and that will be the answer to the question. So thanks for asking. Okay, so, and these jets, of course, are what one is observing at the interface between the wind in this interpretation and the jet. And that interface can be thought of in two ways. One is a boundary layer, like you see in any fluid flow, or as a current sheet, which is a discontinuity in the magnetic field as a current sheet, and it's almost certainly both. And in fact, what will happen, as will happen in a jet, in a jet exhaust or something, is you get entrainment of gas into the. Initially, it's just purely electromagnetic and sparky. Sorry, here it's electromagnetic and sparky. But when you're up here, you've entrained a lot of gas, and it becomes much more a mixture of gas and magnetic field and so on. And we have to rely on the observations to tell us what's going on. So now if we look on the larger scale, up here, then what is happening is there's a continuous inflow of gas from the surrounding cluster of galaxies, And that comes in at high latitude, low latitude, high latitude in the south, and that is ultimately what collimates this outflow. So in this interpretation, the magnetic fields are essentially unidirectional. They're what have collected over time. Gas is continually falling in, joining the disk here at a high rate, and almost all of it is driven off, with the power coming from the spinning black hole in the middle. So 10% of what's in the jet is driving away the gas in the roundest of numbers. That's the story. So, so M87, we claim, is powered by rotational, not gravitational energy. So it's like the sun. The sun in the 19th century was powered by gravitational energy because that was the story, and it should last about 10 million years. And when it was found to be more likely to last 10 billion years, people had to invent nuclear physics, and they did rather well in that context. And so that's how stars like the sun are powered, is by nuclear reactions in the core. I said there was the fourth puzzle I had was, why do elliptical galaxies make jets? And here the contention is, it's not essential, but the contention is, it's because you've got high latitude infall, up here, into this so-called magnetopause. That's a sort of space physics language. There's a high latitude infall here, and so it provides a boundary condition at very large radius. That isn't present necessarily in spiral galaxies. In spiral galaxies, all the gas comes in very low latitude in the disk. And so the outflow tends to be like that, rather than like that. And the boundary conditions really matter, and it's a bit like, a tornado or something, which is usually the bit that lifts the roof off a house. Is very small, 100 meters or something across, but it depends on flows of 100 kilometers maybe. Okay, so, and again, the sort of philosophy is that we're using observations and global conservation laws to think about this problem, rather than treat it as a sort of, and treat it as an inverse problem, rather than treat it as a forward modeling problem. And, so that's just a philosophical thing. Okay, now, I think I'm going to pass on this. I think there's not going to be time, but I can, if anybody, this is sort of a bit more discussion of how the magnetic field extracts energy from a black hole. And unless anybody wants me to do this, I'll happily do it, but I think it's probably best to move on, because I won't get to anywhere near the end. How are we doing for time? Sorry? 10 minutes, then I certainly don't do that. Okay, all right. Okay, so I haven't got to snap, crackle, and pop, so I'm going to take a little longer than this, but I'll do this as fast as I can. I think this is, so let me go through this bit faster than I probably should do. There's an implication of having this strong magnetic field, more than 100 Gauss. And that implication is that the electrons that are emitting synchrotron radiation at 1 millimeter cool very fast on time scales between minutes and most an hour, okay? So they cool very, very fast. And contrary to what happens in the low field models, the MAD models, what happens is that you're looking at a series of sparks, or flares, I would say flares, rather than a steadily glowing thing like the sun. You're looking at these flares, and so because the cooling times are very short, and the way that you get acceleration, the way that you get the particles is that it's just like the sun, where you build up magnetic stresses, then all of a sudden you get a solar flare or a magnetic coronal mass ejection and so on. Those things can happen. The same sort of thing happens. You tangle magnetic fields like that. Then what happens, and there are people here studying this, it's called reconnection. Those field lines exchange partners and simplify. They release magnetic energy, and that goes into relativistic particles, which give you the synchrotron radio emission. An alternative, which is one thing that I think is inevitable in these cases, is something I call magnetoluminescence. And this is as well as having reconnection and an even faster time scale, you very quickly build up slip knots. And if you have stresses, magnetic stresses along the magnetic tension along the field lines, they'll resolve those those slip knots, releasing magnetic energy. And so this is the natural mechanism in a variety of environments within this black hole scenario for releasing energy in flares. And our contention is you haven't got a sort of smoothly emitting region, you've actually got a series of sparks, flares or sparks. Flares from perhaps the sheath of the jet, or from the disk where some gas is flowing inwards, and sparks from the magnetosphere in the vicinity of the black hole that's purely electromagnetic. So I'm just doing the language. Now we go to the next one, which is Cackle. And this is where we start getting into the connection to observations, which, you know, and these are, again, our point is that you can use existing observations in 6 new ways, actually, to search for effects that are implications of this interpretation. So that's where we're going. Now, if you just consider one flare and consider what happens to it, I said the particles cool quickly, but if you just consider a single flare, then generically you expect the time profile of that flare to be asymmetric. And there are 2 ways in which it can end. One is it can expand faster than it cools, or it can cool faster than it expands. Both of those are possible, and both of them lead to slightly different models, but this will happen on timescale, say, of hours, and this is the most simple-minded model, and you can see that's a quite asymmetric pulse. So if you were to imagine that the flares were asymmetric in this systematic way, and at any time you were only seeing relatively few flares, and some of them may be very bright, and those are the ones you catch on, then the way to seek this in the data is go to a 3-point temporal correlation function. 2-point correlation functions will not tell you about the arrow of time, but 3-point correlation functions can. And this is the simplest one to look at, and you can just use, go through existing data. If you think it's the expanding flare, then there will be correlations in frequency too. So if you've got more than one frequency, then you can look for it's a 2-point correlation function with frequency. So this can be sorted in the data, and the key thing for the observer, for radio astronomers and so on, the first thing a radio astronomer will do in these circumstances is remove all the RFI. And most of that will be people fiddling with their cell phones or microwave ovens or whatever. But sometimes they will also perhaps remove signal and so on associated with flares. And there are ways of doing this that will make this much better. So I say, you had a question?
Yes. In the previous slide, you showed this magnetic slip knots.
Yes.
I was wondering what prevented the slip knots from actually forming magnetic reconnection, breaking away?
Oh, excellent question. I'll give you a simplistic answer. The longer answer is I don't know. But the simplistic answer is that the characteristic time scale is the light crossing time across the region for the slip knot. And for reconnection, it is that time scale multiplied by a logarithm. And as Fermi told us famously, all logs are 10. And so this will happen faster. Excellent question. Thank you. Okay. All right. Now, here is my second heavy-duty physics talk. But I'm going to put it here, and I'm not going to have time to go through it. But let me just, this is the simplest way that I can think about describing how to do relativistic ray tracing. All right? So let me just say in words what's going on. Firstly, I believe in the Kerr metric. It's one of the last things I'll question in this business. And there's plenty of evidence that it's right, and I think the microphysics of what goes on in the gas is much more questionable. So let's just imagine a ray of light going through Kerr space-time and then coming to the observer. So what we've got is an observer O here, a source point there, and a ray of light coming along in this direction. Okay? Now, if we back project its direction onto the sky, that's what the radio astronomer sees. That's the picture of the orange ring. This is where the ray actually came, and in order to, it turns out to be, people make great performance of this, but it isn't hard. It's really very simple. There's 4 first-order ordinary differential equations. You can solve them with elliptic integrals or so, but it's easiest to use numerical methods. And there are 3 constants there. One's an energy for the photons, one's an angular momentum, the third is a thing called the Carter constant. And basically, the ray is determined. If you think about this mathematically, if I look on the sky and say there's a vector, if that's the direction of the black hole and there's a vector on the sky, which is where the ray is coming in, that's a vector displacement like that, then there's a trajectory parameterized along the ray that is a function of that position. All right, so there's a ray that comes in. And you can solve for that very simply, and you can think about it not just in 4-dimensional space-time as you do to solve the equations, but in a 3-dimensional space, because everything's stationary. There's a 3-dimensional space, and then there's a time associated with this, which is, if you're looking at variations, that time is important. And the thing about the Kerr metric is the time is a universal time. It's the time registered at infinity. You can then do 2 more things. One is you can calculate along a given ray what the magnification is. Technically, it's the inverse of the magnification, which is something called the Hessian. Doesn't matter. And because it's the inverse, when the Hessian goes through 0, it's the determinant of the Hessian goes through 0, the magnification becomes formally infinite for a point source in geometrical optics. And that's simple to calculate. And the next thing is you can do the polarization, because we've got polarization maps, so we've got to know what the polarization is doing. There's a gravitational rotation of the polarization vector as it goes around the Kerr metric. And so then you can invert, and then I won't say anything about this. I won't interpret this unless somebody else about the photon sphere, because there's been a lot of discussion of the photon ring and photon sphere, and I'm not going to go into that. But the one more thing you need to know, just to get the optics right, is if you've got a source, you've got some, say, moving gas that's moving past this point in space with a certain speed, a full velocity u in the language of special relativity, then there'll be a Doppler shift that takes into account the gravitational redshift and the motion, and that'll give you a Doppler factor shown here, and then that tells you that the intensity is different. The intensity that's observed at Earth is different, and you can easily calculate this. So you just measure these along the ray, and it's very easy to do this for a set of rays. And then you map this space-time, and then you just sort of interpolate on this. It's very straightforward. You can do it on a laptop. So you don't need, people do giant simulations, but it seems to me it's, for these purposes at any rate, it's unnecessary. So what does that mean? So the first thing to say is that if I've got a source there, and say in the vicinity of a black hole, and Prajwal is going to be my observer over there, here's a source here, then there'll be a ray that will leave. If I go backwards in time, it'll leave Prajwal, go past the black hole and pass through this source here. Okay, that's the way to think about it. But there will be, in fact, 2 important rays, one that goes this way and another one that goes this way to Prajwal, okay? So so each source point is connected to the observer by 2 rays. Now, in fact, it's connected. Each source is connected by every source is imaged by every black hole an infinite number of times. But this is just geometrical optics. There's no photons associated, no significant photons associated with it. So there's just 2 rays. So if I consider a generic ray passing through here, what happens is the ray, if I consider it going backwards in time from Prajwal, comes along here, it will go generically through a point where the magnification is infinite or h is 0. The Hessian, determinant of the Hessian is 0. At that point, a source point beyond that point is going to be the image is going to be inverted. So if you look at this conversely, and at the point where h is 0, that is where the caustic is, and this is where the optics comes in. That's where the caustic surface is. So again, if we think about, let's be a non-spinning black hole, in that direction, in the background, it would just be, there would be a line focus behind it where all the rays would focus. If it's a spinning black hole, it becomes a surface, and you'll see that in a moment. So with every source S, if we now turn this upside down, there's a primary ray that's uninverted and a secondary ray that's inverted, and they'll come at different times. That's an echo, and they'll have different magnifications. Sometimes the magnifications will be large. The sort of whimsical way I sometimes demonstrate this is if we imagine in the time of the dinosaurs, us on Earth, somebody, a dinosaur armed with a smartphone or something, taking an image, then there are two ways of seeing what's going on. One is the direct thing there, and the other is the ray that goes around the black hole and comes back 130 million years later. So there's no photons associated with that, of course. But, you know, that's another way of demonstrating that there are two images. Okay, so again, looking for these echoes when they're comparably bright is something you can do with existing data. And this is, you know, this is the sort of schematic. These are the two rays here, for example, showing in a sort of schematic way. You can calculate this. So let's just talk. I've showed a picture of Pancharatnam because it's a tribute. And basically, when you work this out, and this was in a paper that Kevin Rausch, who was a student of mine, he essentially did all the work in 1994. We figured out what the caustics look like in the Kerr space time. And what you see is that what was in just a line behind the black hole, in this case it's shown in the equatorial plane, it wraps around like this, and it has this characteristic asteroid-like cross-section. It looks a bit more like this, close to the black hole. And the point is, when you get very close to this, then the magnification is infinite for a point source as you cross the caustic, but even inside it is enormous, typically thousands or so. So a small enough point source crossing this caustic will make a big bright flash. Okay? And so if they have the caustic crossing, something's gone wrong there, never mind, then you'll create, basically if you have a point source that crosses there, there'll be two images of the source there, which is the regular case, then you create two more images. And you come out the other side, and then your two images, you have a source that crosses the caustic near the black hole, and you'll see a magnification that has a characteristic pattern like that. Michael Berry and Pancharatnam and all that would recognize all of this immediately. And you might say, well, 4 is not very much, but this is a logarithm. This scale is logarithmic. And let's not forget about that. But what you have is, in ingress, you create two more images, and then they're going to fade as t minus 1/2. And then in egress, you'll have two images that will brighten as minus t 1/2 and then vanish. But the thing that happens, which I was trying to show here, but obviously didn't quite show up there, is if we think about what's effectively an Einstein ring around the black hole, then the two images that you create, they're close together, and then they go all the way around the black hole in this case. And then two of them on egress, two of them join up and disappear, brightening as they do. Now let's go back to radio astronomy. Remember the picture of the Earth with those telescopes. You're doing interferometry. And let's not do sophisticated imaging, which is what the AHT team do. Let's just take a two-element interferometer doing the simplest sort of interferometry, the moments of just one baseline with two telescopes and getting the visibility, which is essentially the Fourier transform of the intensity on the sky. that visibility, this is the Fourier transform shown here. And so just taking the visibility data, not taking any imaging that's done with it, just taking the visibility data, which is a raw thing, you should be able to see these bright things running around the ring on time scales of minutes to hours, depending on the particular source that you have. And there are this is something that has a characteristic signature in signal processing, if you like, and it'll be point about this. It'll be if you do it in one baseline, it'll be predictive for other baselines. So you can do this, and then there's implications for polarization and other frequencies and so on. And now, obviously, real sources are going to be large. So this presupposes that there are sparks, essentially, that you're looking at that are small enough that they can be resolved by a caustic. If they're much bigger, I mean, again, we thought about it a bit, but if they're much bigger than the caustic, then you're not going to see anything. Furthermore, and this is rather interesting, is in this limit, your Fresnel length is not that tiny, and so you're pretty close to the regime of physical optics, and so it's a bit more like scattering through the atmosphere or interstellar flicker and so on. So you're pretty close to geometrical optics, which raises other possibilities. So I'm not going to go there anymore. I advertised that I would talk about the applications of this to other sources. I won't do that. As we seem to be probably running out of time, let me just say that, summarize, and I will sort of try and emphasize this a little bit more if you give me time to do this. The HT observations truly are a magnificent accomplishment. And the strong field ergomagnetosphere ejection disk, this model that I've outlined, is an alternative to the standard model. And you can seek in, I think, at least 6 different ways using existing data that's out there in public. I'm working with professional and qualified radio astronomers to try and we're starting to do this. So we're actually looking at data and trying to see if we can, and I've talked to the HT team about this, and they're sort of encouraging, so they're not. So you can look for the arrow of time in the flares. You can look for the arrow of time in the echoes. And the twinkles, what I call the twinkles, these are the little sparks which might be giving you these spikes of magnification and the visibility patterns that I outlined on timescales perhaps of minutes, maybe. It depends where they are. There's many places they could be. And the philosophy here is if you ever found any of these effects, it would say the field is strong. And furthermore, it will be pretty clear where the emission is coming from. So it's an inference of where the emission is coming from rather than assuming, they literally do 10 to the 5th images when the numerical simulations and then compare them systematically with the data. So this is a very different approach, if you like. And if you found it, obviously it would tell you about the microphysics and so on, and would enable you to measure the mass and the spin and the angle and so on in principle. And then in principle, for those who doubt, confirm or at least be consistent with the Kerr metric. But that's sort of long way down the road. I mean, the first thing to do is to find any of this and see if there's any of this there from any of these simulations. And if nothing is ever found, then I think, probably it'd be true that it would be, I would argue that the MAD models were right all along, and and it's a low field environment, and you're looking at a steady glowing thick disk of gas. I mean, there's physical reasons why I disbelieve it, because I think the coupling of the hot ions to the electrons is much faster than it's just plasma instabilities, and the electrons are heated very fast, and they cool the torus very fast, so the whole thing deflates like a balloon. Anyway, so that's where I'll finish there, and I thank you very much for the invitation to give this talk, and welcome any more questions. Thank you very much indeed.
Thanks very much for waking us up out of our complacence in interpreting the ring and the silhouette. So, yes. Okay. Can Mayuri have the mic?
Thanks for that. I had two questions, quick ones. You mentioned something about retaining the raw data because a lot of things get thrown out as RFI. But clearly, these phenomena would also have some spectral signatures which one could use to distinguish RFI from the flux from the source itself. Yeah.
I mean, yes, I'm willing to learn, but at this stage, I regard myself incompetent at that. And for those who don't know, there's a thing called a fast radio burst. And to the eternal embarrassment of radio astronomy, radio observatory directors, many of the signals that were found were discovered to cluster around lunchtime. And it turned out to be a microwave oven that was producing it, but not all of them. And so the others come from the other side of the universe. So it's a serious issue.
Yeah.
But there are very straightforward ways of saying if it's real or just more interference.
And the second follow-up is when looking for these like time-scale related events, are there specific regions around the black hole where you would expect to find this more of, or we don't have the resolution to kind of tell them apart?
I would, again, taking this sort of empirical inferential approach, I would say there are good candidates. For me, I would say the sheath. Remember, we're looking, you can be the observer now, and there's the jet. You're looking at the small angle of incidence to the jet, the approaching jet, and indeed the receding jet. And so the sheath could well be a source of flares. And that's a good place to look. You've got a differential flow. And, reconnection and magnetoluminescence and all these sort of things are going to accelerate. It's almost inevitable that it's dissipative. The second place I would look is in the equatorial plane, where there will be some gas. I'm saying we're going to blow away all the gas. We're not going to blow it all away. Some will get in for sure. And there will be dissipation associated with that. And there's this governor mechanism, which I didn't go through and won't, is going to also be a source of electromagnetic radiation. So in the equatorial plane, it's the second place I would look. And then the third place, particularly for the caustic crossings, I think, because I think this is where you're going to get the smaller sparks, is going to be in the base of the jet. That's where you get the small sparks.
Practical question. I was wondering what was the integration time for the mic is not on. Pardon me. So I was wondering what is the integration time for the image of the M87 black hole and how would it compare with this? I mean, you're talking about your integration times to observe a twinkle is of the order of minutes, to observe a flare is of the order of an hour.
No, it's very short. It's very short, yeah. And it's dependent on the bandwidth, and it's a longer answer, but it's very short.
Sorry, what?
Yeah.
And about the amplitudes and.
Yeah. There is an issue with doing the imaging.
Yeah.
And that is really the variability. In something like Sagittarius star, it's a real problem because if you want to get the full visibility as a function of baseline,
Yeah.
And the Earth is rather slow. It takes 24 hours, it's said, to orbit, to turn on its axis. And Sagittarius star didn't know that, and it's varying rather rapidly on that time scale. M87, which is 1,000 times larger, varies more slowly.
Okay. All right.
Thank you. I have a question in context of general astrophysics. So from this particular example of M87, it looks like magnetic fields are shielding this black hole in form of this ejection disk and is not letting it to feed actually and grow in mass because
Right.
the Eddington rates are so low. So can this be a mechanism to actually bound the mass of maximum mass of massive black holes in centers of galaxies? Maybe it is something related with the environment that you were talking about, maybe spirals versus elliptical. Yeah.
Yeah, okay. Let me use another folksy metaphor. As any parent of a young baby knows, if you feed them too little, they starve. It's very unhealthy. If you feed them too much, they don't accept it. You have to feed them at the right rate, and then they grow. And so it's the stage of intermediate mass supply. And these black holes have to grow. I mean, they start off small, and they're billions of solar masses in the case of M87, so they've got to have grown. And it's probably happened about 3 to 10 billion years ago, all of this happened. And so what limits this now is really the supply of gas. I mean, basically, you run out of gas in most of these things. So the reason why M87 is being starved of gas is not a cruel mother. It's because there isn't so much gas falling in as there was in the past.
Thank you.
And also it needs more because it's bigger, it has to eat more. I mean, that happens too.
I have a very general question as a person who is not working in astronomy. Studying the black hole, which is right in our universe, does it give a comprehensive knowledge about black holes in general, or there are other black holes in other galaxies which can give us answer more open questions in this field?
That's a very good question, so you should join up. Okay, the astrophysical black holes are basically determined by two numbers, two quantities. One is the mass, and that's purely a scale. So if we go from 1 million solar masses to 1 billion solar masses, we are just increasing the timescales and the energies and so on involved. So that's purely a scale, and that's nothing particularly important. The other thing is this spin parameter, which I called A. That is something that differs from one black hole to the other. Beyond that, and this was the great miracle in some sense that Roy Kerr brought about, was it's almost proven for the standards of mathematicians, and certainly well enough proven for the standards of astronomers, that this is all there is in astrophysical black holes. Now, you can have more types of black holes, for example, with charge in them, but under astronomical conditions, that charge is never important. But in the, as I say, the febrile imaginations of theoretical physicists, considering those black hole spacetimes with charge has been an enormously fertile and question-posing environment, and so it's been a great gift to the people who first started thinking about these solutions. And in particular, the subject of this conference that we've been at, the interface of that with quantum mechanics has been where the action has been, and it's been very fertile. But in terms of astronomy, we do not expect them. So it's really, there's just one number that is different between one galaxy and the other. And so they really should all be the same. Now, if you find the black hole in that galaxy is totally different from the black hole in that galaxy and so on and so forth, then all of our precepts from general relativity and the Kerr metrics and all of Kerr spacetime, I should say, and all of that have to be re-examined. But there's no evidence of any of that as yet. But it would be lovely to find it. Thank you.
Carrying on from that, I mean, is there an analog situation, astrophysical situation with stellar scale black holes, which can be studied more, nearby and even more detail? So
They were on my list there. These are the galactic black holes. There are many 30 in our galaxy, for example, that are in binary systems.
yes.
Where the binary star essentially gives gas, like on a much larger scale, and there's, say, something like a 10 solar mass black hole that's receiving it. There's a range of, obviously, examples that are seen. And some of those make jets. And those jets are qualitatively similar. There are some differences, but qualitatively similar to the ones that are seen in active galactic nuclei. And I like to call these quasars for the impatient because, of course, the timescales are very, very much shorter. So you don't have to wait a million years to see a full cycle of, you can see it on, in a graduate student's lifetime. So we've learnt a lot from those. And now there are some differences which we sort of understand, but there's more things that are similar, and they're teaching us a lot, as indeed are these other examples. Even neutron stars make these jets, and they're surrounded, I might just say, as being verified recently, with extremely well-organized magnetic field. It isn't just a tangled mess of rat's nest of magnetic field. There's large-scale current flows light years away from the central neutron star. So that's the precedent for making these large-scale magnetic fields, which we assert, collimating the jets.
But the silhouette is a distant dream, right? Stellar black hole. We can't get the silhouette.
You mean?
We can't image the ring.
Oh, no, you won't image the ring. Sorry, no, not now. No, you're way out for that. One of these ones, I'll just say parenthetically, I have been working on with a colleague who's done magnificent observations, and it's called SS433, and that's a black hole in a binary system, and it's had a lot of puzzling behavior. And her observations, I think we can now model it very well. It turns out not to be a binary, but a triple. So, yeah.
I had one more question.
Yeah, okay,
A
right.
quick one. I mean, you mentioned a lot about Kerr metric being right. So I just wanted your perspective on how important do you think LISA, which is supposed to map out the space-time around these massive black holes, through the, mapping the orbit of a falling in object, how important would that be in the scheme of things in terms of verifying something like the Kerr metric?
Well, the Kerr metric is stationary and axisymmetric in an asymptotically flat space-time. And so it's basically, approximation, and it's nowhere near the relativistic situation of two merging black holes or black hole and neutron star or whatever. And so that's dynamical general relativity.
No, so I'm talking about the case where a small black hole or some object, compact object, is falling into a massive black hole. And what I understand is the waveform that LISA will be able to see allows you to map the entire space-time around this massive black hole, because you see how the orbits decay, and you can map the entire space-time. Is that something that would be relevant?
Again, I'm not. Again, I guess it comes back to this business of forward modeling versus backward modeling. If I put in the curve, some version of the curve metric for a Kerr space-time, and compute the waveform, that's sort of automatically put in there by general relativity. And so we can say, is the general relativistic calculation consistent with the data? And so far, we've no reason to doubt that, but in future better observations, especially from something like LISA, you may well find that's the case. That would be very wonderful if true. But if you say, can I, from observations, go backwards and infer the Kerr metric, I think that's, you can fit a parameter which is the spin. You can fit the parameter which is the spins. But beyond that, I don't think you can really, you can get a whole family of different metrics, and you could say, set all the parameters in that family of different metrics equal to the relevant values. That, I think, would be very hard to do. Maybe somebody has done that, but it's certainly beyond anything I could imagine doing.
You mentioned that the rotation rate was 90% of the maximal. Is that right?
Oh, that was pure conjecture. And if you ask me to defend that, I shall blame my colleagues, because I have no way of defending that. Okay. It's just an educated guess, no more. There are some people who do simulations with a maximal curve. It really doesn't actually matter too much, because for the geometric optics, what matters is the component of spin perpendicular to the line of sight. So in this case, it's essentially it's the same as a spin of 0.3 looked at optimally from the equatorial plane. So we kind of know that the scaling laws depend on a sine theta.
Well, so you mentioned these quantum effects that happen for charged black holes.
Well, they happen for uncharged black holes as well, of course.
Well,
yes.
they also happen for rotating black holes, and
Yes.
they become extremely strong near the maximal. So that's why that's
Yes,
quite interesting.
yeah.
And so is this, are the other black holes that are also close to maximal, or is this one of the best?
Oh, okay. I'll wear my astronomer's hat. There's observations out there from what's called reverberation mapping of Cepheid galaxies where it is claimed, somewhat controversially, that many of them have spins pretty close to maximal, like 0.98 or 0.99 or so on. I'd love that to be true, but I'm a curmudgeonly old skeptic that they really quite know this. I mean, it's heroic stuff they're doing, for sure, but I'm a little bit worried about, the things that could be, the systematics that could be in those interpretations. But there are people who claim that the spins are that way. And I would say, on astrophysical grounds, it's awfully hard to spin up a black hole to anywhere near Kerr, because every time you try and throw more angular momentum at it, it ends up you're giving it too much more mass, and so it's terribly hard to find just the right trajectory for some mass energy to go into the horizon to spin it up. In any sort of phase space argument, then you're never going to get anywhere close to A = 1. So you need engineers.
So I had a question that the 0.9 value of that maximal spin, was that taken fiduciarily or that calculation?
Taken fiducially, what we did was we said in order to write a paper of finite length, we will just do the fiducial model and put all the scalings or whatever and the examinations of other possibilities outside, in some supplement or something. So that's what we're doing. So that's fiducial. And I should say it's not as extreme as it might sound, because it turns out for these purposes, the more relevant kinematic quantity is not the angular momentum per unit mass, but the angular frequency. And the angular frequency for an A of 0.9, a maximum, is 0.6 of maximum. So the angular frequency is 0.6 of the maximal value. So it's a modest value, and quite reasonable for what would have been left behind by some early high mass supply rate of growth of spin. And the thing is, gas that plunges into the black hole has more specific angular momentum than the holes typically. And so it's generically going to spin it up.
Okay. And I have a quick follow-up. So currently only 2 sources can be observed with the current EHT. Do you have any comments about the upgraded EHT, that like the next generation EHT or like some black hole telescope that has been planned? Like what kind of avenues can that open?
Yes. Okay. There's 2 things that are happening. There's a next generation EHT, which is more ground-based, so it's more things like Greenland in warmer places. And that will be great. I mean, all of this is great. The thing that they're working on at the moment is, I think it's BHEX, Black Hole Explorer, and I think there's a proposal that's gone. I'm nothing to do with it. I haven't seen the proposal. I don't know. All I've heard is enthusiastic talks about it. I'm wildly enthusiastic about that too. I've been sort of on the fringes, if you'll excuse the expression, of space VLBI since the 1970s, and to get, there's been 2 things that have been done that have been spectacularly good, but this doing at millimeter wavelengths would be transformational. You won't get much more baseline, but you will carpet the UV plane. There's a Fourier transform plane. You will carpet it, and so your imaging will get so much better. And so I'm wildly enthusiastic. What they're developing it for is for seeing this so-called photon ring, which I skipped over. And there, you can just say I'm an old curmudgeon or whatever, but this is terribly hard to see, and it depends on getting photons go round and round in circles and on a very small set of orbits, and those photons not being absorbed. There's a brightness temperature limit, which in their models is quickly encountered. So you can't go around too many times, and it's not very many. And just instrumentally, I think it's going to be terribly hard to see it with this. But, but I wish them luck. I'd love to be wrong about that. But unlike other sort of, out there experiments, this one can't fail because it's going to, do so much of the rest of VLBI so much better that it, if it's supported, it can't fail to deliver discovery science.
Okay, we'll have one last question.
Thank you, Pradhan. Thank you. Nice talk. Just wondering if the conventional imaging algorithms may need to be modified if you have to take into account these echoes and.
So what
the imaging algorithms, unaware of any of the artifacts that may come in the visibilities. So the images that are produced currently,
the images that are produced are by and large not. I mean, they don't have to. I'll give you a sort of simplistic answer. If I've got a gravitational lens and I've got a and behind, you're the observer now, and behind there's a uniform brightness. What you see is a uniform brightness, if it's just a simple static gravitational lens.
I think he's referring to the time variability.
The time variability. Yeah, but
impact on the Fourier transform.
well, it is, but this is a problem before you get into echoes. It's a problem for Sagittarius star because the timescales are the characteristic timescales are more than 1,000 times shorter than the ones we're talking about in M87. So whatever's orbiting around you're looking at is 1,000 times shorter, and whereas that might be weeks in M87, it becomes less than a day, and that's the timescale for the Earth to orbit and for the baselines to change between the telescopes.
So one quick follow-up question. Are these voltage data from the VLBI telescopes available on a public domain?
Yes, that's what we've discovered. That more of it than we thought is actually available. However, you need a good guide to be able to know how to use it. And I'm, working with some radio astronomers who know how to actually use it. It's just beyond me to know what to do next, but they do know, and we can at least start to try and look for some of these effects. Quite how much I just don't know. This is an exploration as far as I'm concerned. But I think it ought to be possible using, not waiting for the big interferometer in space, but looking for just looking using existing data. It should be possible to look for some of these things. But give us a few, 3 months or something. I suspect we'll have a much more sophisticated view of what's possible.
Okay, I think people should feel free to ask questions to Roger during tea, to which we will go now. But meanwhile, thank you very much.
Thank you very much. Thank you.
To add a few nice things to your luggage.
Oh, okay. Oh, sorry. I'm just doing something with the slip knot on my shoelaces. Okay, thank you. Oh, wow. Oh, thank you. Thanks, Jonathan. Yes. So he was a great man. Okay, lovely. Yes.
This is a sketch made by one of the visiting astronomers from
Who is
Arizona State it's from Rice University.
You know who it is?
Mustafa.
He was my student.
Oh, Mustafa was.
Yes, I have many of his pictures in my home, including one of the arch in Mumbai.
Right away.
Yes, so Mustafa's my. He was one of my first students at Stanford.
Oh,
so I'm really glad to see it. Yeah. Thank you. Oh, thank you. Wow. Mm-hmm. Oh, yes. Oh, wow, yes. Yes. Oh, thank you. So I have another book on C.V. Raman, a biography, but this one is different, so I look forward to it. And I enjoyed the other one. Yes. Oh, well, thank you very much. Yeah, yes.
The other one probably has a lot more stories.
Yes, no, well, thank you so much. Thank you. Wow.
Is the collected works of
Oh.
Ratnam for you.
Oh, oh, yes. Thank you. Well, like Michael Berry, I shall probably see a full discussion of caustics in Kerr-space time in this book. Yes.
And finally, you know, we.
Oh, GWC. Oh, yes, yes, yes. That's good.
The
Yes.
completed 75 years. And
Oh,
brought out
congratulations.
a little thing which is highlighting
Yes.
16 of the major results that came out of this.
Wow. Well, you have more than that to be proud of. So, thank you very much. Thank you.
Thank you so much.
Thank you very much.
Thanks everyone for coming and he is
No, I think I can manage it.
Okay.
Yes, I came light as long as